Section 2.6, Infinite Sets. Most of us are familiar with the symbol for infinity, and maybe we thought that infinity was a number. In fact, infinity is not a number. We would say infinity is more of an idea. And the idea is that it is an amount that cannot be counted because it's so large. Perhaps when you were a child, you played the game of thinking of the largest number that you could, and then your friend would just add 1 to that number and think of a larger number. Well, it's the same thing. Infinity isn't a specific number because no matter what number you think of, if you think it's the largest number, 1 can always be added to it, or 2 or 3. We can always add to it to get an even larger number. So it's more an idea of a quantity that is so large that it cannot be counted. For instance, the number of stars in the universe cannot be counted. Therefore, it is believed that there are an infinite number of stars in the universe. So, an infinite set contains an uncountable number of elements. Now, how do we show that a set is infinite? One way to do it is that an infinite set can be placed in a one-to-one correspondence with a proper subset. So notice this set here is within the set. So it's a proper subset. It's totally contained within the set. So if we can create a relationship like this, we can show that a set is infinite. Now, how do we actually do that? Okay, let's take the set of natural numbers, 1, 2, 3, 4, etc. A proper subset of the natural numbers, and you can pick any proper subset you like. I'm just going to pick the easiest one. I'm just going to leave 1 out. 2, 3, 4, 5, 6, etc. We can put these sets in a one-to-one correspondence. And the way we'll do it is creating an input-output table. So if you took Math 021, here's the use of input-output tables coming back to us. So let's list the natural numbers, and let's go list the proper subset as the output. And we'll see that 1 goes to 2, 2 goes to 3, 3 goes to 4, etc. So this is what I mean by a one-to-one correspondence. Each number in the first set goes to a number in the second set. The first set being the set of numbers we're wanting to show is infinite, and the second set being a proper subset of that. Now what we like to do is come up with the general term. And the general term is always related to the natural numbers. So this is convenient in our case because the set that we're trying to show is infinite, happen to be the natural numbers. So we always have to have an n here, and then we'll write the formula. Another name for the formula is the general term in terms of n. So what did I do to go from 1 to 2? I added 1. What did I go from 2 to 3? I added 1. What did I go from 3 to 4? I added 1. So what did I go from n to here? I added 1. So the general term for this is adding 1. Okay, so for the first set we had n, and for the second set we had n plus 1. These are what we would call our general terms. Okay, let's look at another of these. Let's take the even numbers, 2, 4, 6, 8, 10, etc. And let's go ahead and pair those with a subset, a proper subset of those, 4, 8, 12, etc. Okay? So we have our even numbers listed